Hello everyone. I am Charul. I'll be the instructor for this second section on dimensionality reduction. I'm an applied scientist at Amazon. I build ML models that predict returns, identify why they happen, and thereby helping sellers and shoppers make more informed decisions. This is section 2 of dimensionality reduction, and here we will discuss the feature extraction techniques. In the previous module on dimensionality reduction, we have discussed the feature selection techniques. Right. The first question is why do we need feature extraction? So there are multiple examples, and a few of them is in recommendation, genomics, and face recognition. So let's see the first recommendation system. So in a traditional recommendation system, we have a user cross item matrix, and few of the entries are present for this matrix. Rest are missing, and the information that is present in this matrix can be rating, can be click, or any other information related to the product that is captured by the users, right? So the overall idea is that only few of the entries will be present in this matrix, and the rest would be missing. So we can use matrix factorization to learn the pattern between these users and products, and in way try to predict the entries where the data doesn't exist. The second is genomics. So basically, you have a very high dimensional SNP measurements as features for different people, right? And what we want to do is we want to identify the clusters, and you don't have the actual, labels available. So with PCA, you try to find the principal components, which summarizes or provide the information of this all this high dimensional SNP data well. And when you visualize it, you are able to see the clusters that provide ancestry information or patterns in the data. Then we have the face recognition problem. So suppose you have a lot of face images, and every image is 64 cross 64 pixels. So now, if you make this as a matrix, so your one of your column will contain all the face, image pixel data, which is 64 plus 64, and you have n such columns for all these faces. Then you run the PCA on this data, get the eigen faces that captures the direction along which these faces vary, right? And now any face can be a weighted combination of these top eigen faces. So overall, the idea is for high dimensional data, we have a few dimensions that carry the majority of the information, and we will discuss how to extract those features and the corresponding techniques in this lecture. So overall outline of this lecture is divided into two parts. The first is to reduce the high dimensional data into K dimensions using SVD, PCA, matrix factorization. And second is how can we visualize the data in a 2D space using TSNE and UMAP. So let's start with SVD, Singular Value Decomposition. So a very popular problem, the Netflix problem, which began in 2006, and Netflix provided the data set for an open competition to improve its recommendation algorithm. So this data set contains roughly around 500,000 users, around 18,000 movies, and only a subset of the entries are observed in this data set. So the question is, do we need all the entries in this matrix? Right? There can be clusters of users and movies to estimate the missing entries in the matrix. The question is, can the rows and columns of this matrix can be written as an combination of small set of bases or vector that contain majority of the information. So SVD can help find such bases. So the idea is most of the information in a real matrix, a very high dimensional matrix, lives in a small number of singular values, right? So not just the Netflix problem. Suppose you also have a sensor readings across multiple locations, right? So for a timestamp, there'll be some, M locations on which you take a sensor reading of temperature, of pollution, whatever measurements you want to observe, and across different time periods, you record this reading, right? So what happens is this seems like a high dimensional data, but there is correlation and information involved in it. So like locations data would be correlated, temporal data would be correlated. So we don't need all the m and n dimension to actually capture or have the information of this matrix. We can find a small set of basis vector that contains this majority of the information, and we will see how we can do that using SVD. So any matrix X, we can write it as U sigma V transpose, where U are the orthonormal left singular vectors and V is the orthonormal right singular vectors. And sigma is M cross N matrix, which is diagonal, and it would be a minimum of M cross N, otherwise it would be zero. But not only just the minimum of M or N, it can also have less than that entries. Like, there can be R non-singular values. Rest can be zero in this matrix. We'll see later on how this, how this R plays a role in extracting the information. We'll see that more in truncated SVD. Right. So, right. So now we have this X, which is a rectangular matrix, and we want to get this U sigma and V transpose for this matrix, right? So what we have seen is eigen decomposition, but eigen decomposition exists for a symmetric matrix, right? So what we can do is we can take X transpose X and X transpose, and sigma I square are basically the eigen values of X transpose X and X transpose. So even though X is not a square or symmetric, but we can do the eigen decomposition of these symmetric matrix to determine the U sigma and V transpose. So this is a way to our iteration method to compute the SVD. So as we have discussed, so what we do is we start off with X transpose X and X transpose, right? And now the sigma I square are the eigen values of these matrix. Now, what we do is for k is equal to 1 to, for different iteration, we try to first identify the first eigen vector of A. A is basically X transpose, and the corresponding eigenvalues and V1 as well, right? So what do we do is we for k multiple like iteration, we compute this eigen vector, and at the end this would be the first eigen vector, which is UN, and then we compute the first eigen value, which is under root because this is sigma I square, right? So then we have the first like V1. So once we have estimated the first, eigen value and the corresponding eigenvectors, what we do is we remove that from the matrix and then try to get the second eigenvector and the values, right? So, right. So this was like we have in the SVT, we have factorized this M cross N with a U, which is N cross M, and a V, which is N cross N, right? So what happens is that we don't need all the info. So this represents the higher this singular values is, the more information it contains about that basis. So what we can do is we can take the top k singular values and discard the rest of the singular values. So this then this SVD becomes a U sigma V transpose, where U is N cross K, sigma is K cross K, and V is K cross N. Right. So in this case, the actual storage or the entries in X, which is M cross N, is now K plus NK plus K square, right? So we need, if the K is 50, then for 1,000 cross 1,000 matrix, then we only need about like 10% of the data to get all the information of this matrix X. So now let's see how this K varies for different matrix, right? So if you see an image, which is here, and if you see a random matrix with a Gaussian noise here, and we try to see the singular values of these matrix. So what do we see is that since this is an image, there is data correlation, some structure to the image, right? So the data, the singular values, the top singular values contains, majority of the information, and we see this sort of a, plot for the singular values. While if the matrix is random or have a Gaussian noise, then we cannot have a subset or like a K which actually contains all the information of this matrix. So for this matrix, we need to have higher Ks, or maybe most of the information has to be retained to reconstruct this matrix back, right? But for this sort of a matrix, where there's a structure involved, we can take top K and represent our image with those top K singular values. We can see this with an example, right? So suppose you take this original image, right? And then you try to do this SVD decomposition, and you take the top K only, right? And reconstruct the image back. So this is what it looks like if you take K is equal to 1 and 5, right? And 20. So what this shows is the reconstruction error between the actual image and this reconstructed image, right? And then we have how much information is sort of captured by these singular values, right? So if you see the error is high for a lower K, we have around 90% cumulative singular values. But as we keep on, increasing this K, the reconstruction error decreases and we have more information in this image. And if we take it as 40, we have reduced this to a lot, right? By the way, this is a log scale. So so you can think of it as a steeper, more steeper decay, right? So with K is equal to 40 or 80 also, you are able to sort of get this image back, right? So this is how you can think of truncated SVD. Another example you can think of is a term cross document sort of a matrix, right? So, what do we do is now if we take the top k singular vectors here and we say that k is the number of topics you choose to keep. I mean, the k becomes the topic, and suppose this k is 5, and if we try to do the truncated SVD on this, we sort of get clusters, right? So this air pollution environment is in one cluster with this document, right? So we got some 5 clusters in this terms and the document matrix. So the next is the principal component analysis. So we have discussed SVD. So PCA in one line is SVD applied to the centered data. So the idea is like with PCA, we want to find the direction of maximum variance. We'll see how we do that. So suppose we have a data matrix X with m features and n samples, and we want a small number of directions much smaller than the m that captures most of the variation in the data. So the idea is you first subtract the column mean. If you don't subtract or center, then the top singular value vector points to the mean, right? So but we want the variance and the variation, right? So what do we do is we center the data first, and then we run SVD on top of the center data, and then basically we can do the same sort of a truncation, pick the best top k or top r principal components that can give information of the data. So let's see that with an example. So the idea is that we want to find the direction where the data has the maximum variance, right? So suppose this is a 2D data, and we sort of have this um, uh, data line around the x or y coordinates, right? Now, if we want to represent the data by one of the x's, then we'll pick the PC1, right? But that doesn't represent the data very well because there is a variation along the y-axis as well, right? So for any point, we need both the principal component. Principal component one has around 60 8 or 69% or 70%, and the other one has around less percentage of the data. But to represent it, we need both x and y. Now, if we do the principal component analysis, right, and try to find one direction, right, so this is what we get. Now the data is this is the direction with the maximum variance, and this has around 91%, right? Is captured in this direction. And the second direction is, of course, it's is important, but the information is less in the second direction. But note that these two are orthogonal directions. Coming back to the second dimension, the principal component. Now the variance have reduced for the second direction, and it has gone to 8. So if we want to represent this data just with one principal component, I mean, this would be the principal component, right? And you can also see the residuals right now. The error is the residual is lower if we got the right principal component for this data. Otherwise, we are having the high residual reconstruction error, right? Another example you can think of is basically a flower classification problem. You have multiple classes, and you have sepal length, sepal width, petal length and petal width as, 4 features, right? And now the question is that can we have, lower features, like maybe a 2D in the 2D space, like one or two principal components from which we can, classify these flowers better, right? So if we try to do the PCA on that data set, so what do we see is that the principal component one carries, majority of the variance, which is around 73%. And if we add the other second principal component, that has increased to 95. So for the first principal component, you are able to, classify this completely. However, this is not. These two classes are not well separated, right? But with the two principal components, you have around 96% of the information which is captured, right? And the rest are they have less. So with two principal component also, we can sort of represent this data. So now, another example of PCA is the popular eigenphase problem. So this is a data set of around 40 people, and each image is basically a 64 cross 64. So basically, for every person, we have around 4,000 dimensional features, right? So this is like 4,000 cross 40 is our matrix that we are talking about. On this matrix, if we run, PCA on the centered image and, select the top principal components, that is what we call as eigenfaces. And it captures the direction along which the phase varies. So this is your mean phase, right? And then as we keep on checking the principal components, for the initial principal components, we'll see more global sort of a pattern which exists in the phases. And as we keep on increasing these principal component, we see more and more granular and finer details, right? So that's how we get the eigenfaces or the information of the faces from the data using a PCA. Now, for a given image, right, at a test set, if we have an image and we want to represent that with some sort of a principal components, and we see that if we take one principal component, then this is what we get as a reconstruction image, which is not a very good proxy of the original image, right? But as we keep on increasing this, principal components with even 50 or 150, we are able to see that the reconstruction is quite close to the original image, right? So means that we don't need that 64 cross 64 dimensional vector, right? With a small dimensional vector, we can sort of reconstruct the image back, and that contains the maximum information about this data and the image. One more way that people have used is for denoising also. If you add a noise in this image and then you take the principal component and reconstruct it back, you'll get a cleaner image because most of the noise would be captured in the last of the principal components, right? So if you take the initial top K principal components and then reconstruct your image back, you'll be able to denoise your image. So in the literature, people have also, showed this PCA as an encoder-decoder sort of view, this is a linear, auto encoder. So you start off with a m-dimensional, image or a data set, and you get the R or the K dimensional, smaller set. And then basically from that smaller set, you multiply and get the m dimensional signal back, right? So now let's think that this PCA is sort of linear, right? But the high dimensional data, text embeddings, these image embeddings can lie on a very curved sort of a manifold, right? So the question is, are there ways to find this non-linear low dimensional manifold, right? So like for example, for this, I mean, with first principle, I mean, you won't be able to find the linear subspace, which can sort of, help divide this data into these classes where, yellow is a different class and blue is a different class, right? So, right. So for this, there is kernel PCA, right? So the idea is that in this space, this data is on this curved space. But if we project this data to a higher dimensional feature space, then in that high dimensional feature space, the data can become linear. And there, if you apply PCA, we'll be able to get the information back, right? So there's common kernels which is used in the literature as RBF, polynomial, and cosine kernels, right? So then basically you do this kernel and then you center the data and do the eigen decomposition on this kernel. Right. One more interesting thing is that if you look at the maths of this, so this kernel is basically a dot product of this, phi, xi and xj in the transpose in that high dimensional space. So it becomes a dot product, and then the computation is simple, and you can apply the PCA for this kernel in this kernel space. So coming to an example here, right? So suppose we have this. So this is the data we cannot, sort of do the PCA and try to, get these classes separated. So let's suppose this again, we have plot this data like this. Suppose this is the data that we have. Now, if we map this data to a high dimensional space, which is 3D, which is x square under root 2xy and y square, and map every point to this 3D space, right? So what do we see is now in that 3D space, if we can have one principal component that can separate these two classes, right? So this is how we can apply, PCA to a curved manifold. The idea here is that we need to decide and think what are the best kernels to use for our data set, so that, in that higher dimension space, we can find that principal component which gives the maximum information about the data. So, right. So till now we have discussed SVD and PCA, right? But and assumed, that we have all the information available in a matrix, right? But usually we don't have that information available, right? As we see the user item matrix in recommendation system, right? So we don't have all the data available for the rating, for the clicks, we have partial observed data. So for that cases, we have matrix factorization algorithms available in the literature. So, right. So as we see, right, so this is a user cross item matrix. We only observed, a very small number of data in this matrix, right? And this matrix, we can call it as a low rank. Now, the low rank means this R is less than this M and N, right? And why it's low rank? Because there is a correlation that exists in these users and these, movies, right? So that's why it's a low rank matrix. Now, what do we do is for every matrix, we have user vector P and item or a movie matrix Q. And what we try to get is these factorize this R on whatever available samples that we have, try to factorize it into P and Q. And once we have those factorized uh, matrix available, we can dot product and try to fill these rest of the entries in this matrix. Right. So now one thing is that in actual matrix factorization, PCA, SVD, we don't have any assumption on the entries of these matrix, right? But if we add a constraint that these entries must be non-negative, then this is non-negative matrix factorization. So the idea is that if there is a negative term or the entries, so the next the next decomposition can subtract that component from the matrix, right? So what do we want to do is we want to find some sort of a non-overlapping additive component from the matrix. So we can see that with an example of the eigenfaces that we see before, right? So like suppose when we are using PCA, this nose is sort of negative, right? So what this principal component will try to do is it will try to remove this information from the matrix, right? But if we do the non-negative matrix factorization, then all the part is, sort of all the components are sort of, additive, right? So you don't remove any component, nose or mouth or any information which you have captured before, from your data, right? So you get non-overlapping and additive components that you can use. So another example is using it for the topic modeling, right? So now we don't. So for a given topic, we don't want to have any negative term or in that topic part. So there it intuitively makes sense to have this non negative matrix factorization, right? So we can see that with an example here, right? So, the first topic can be this one where the majority information is in books and the rest of them can be reading, written, and authored, and all these are sort of additive uh, uh, terms for this topic, right? If there's a negative term, then it's very difficult to put that interpretability into this topic sort of a model. So here the non-negative matrix factorization helps. So now let's move to the next topic, which is the non-linear visualization. So till now we have studied PCA, right? And we can do PCA and try to visualize the data, but that's a linear method, right? And we have seen that it fails on a curved manifold, for which we also discussed kernel PCA, right? But for the kernel PCA, also we need to define the right kernel for the data. So there are some non-linear popular visualization methods, which is TSNE and UMAP, and we will discuss that in this lecture. Right. So firstly, like, why do we need nonlinear visualization? So, plotting the data and seeing, right, helps in visualizing and understanding the data nuances. People visualize the cell data, right, the clip or dino, image features. So, analyzing and visualizing those features help understand the embeddings of the model better. Right? And as we've seen, right, uh, PCA can work for the linear data, but for the curved manifold, PCA can take a hit in explaining the data well, right? So we will discuss TSNE and UMAP in this lecture. So the first is the TSNE. So there are three steps. So first is getting this high dimensionality similarity. So for every pair of original points xi and xj, we compute a Gaussian similarity, right? And that's higher when the points are closer, and it's smaller when the points are far away. And this sigma I is the hyperparameter, which is perplexity. We have seen in the TSNE implementation, right? So think of this distribution P like as a probability distribution over the pairs. How likely is J is a neighbor of I, right? So this is in the original feature space. Now we have this low dimensional similarity. So we embedded like every the points in, like, now we want to embed it in like 2D. So for every pair yi and yj, we compute this student t similarity. And the reason is that 2D cannot hold as many neighbor as high dimensional. So student T distribution helps with such heavy tails than the Gaussian, right? So we get this high dimensional similarity and this lower dimensional similarity, and then we try to minimize the KL between the two, right? And so this y's that comes out are 2D embeddings. So the whole in this algorithm, so what we try to do is we want to build the queue for the embedding, and we want to move the embedding around such that the queue matches the p distribution, and this is done by the KL divergence. So let's understand the KL divergence for this. So think of KL divergence as how much information we lose when we approximate one distribution with the other. Here, the expectation is done over the true distribution, right? And Q is your approximate, model prediction here, right? And it is a non-negative and asymmetric. For asymmetric, we see in the next slide how this forward and reverse KL works. And there are two related quantity with KL. One is the entropy. So it's like the bits to encode the samples from P, right? So think of it, if this P of X is, for binary 1/2, it would have the maximum entropy. And the cross entropy is the bits required to sample from uh, Q from P, but you're using another distribution Q, right? And if you see this with maths, you'll understand, that cross entropy comes as entropy and the KL divergence. So when this P is fixed, one hot label, so essentially the minimization of this cross entropy is minimizing this KL divergence. So let's try to understand this reverse and like forward KL and how this is like asymmetric. So given that you have a true like a target distribution, the true distribution, which is bimodal, right? And you want to fit it with a uni model distribution Q. So if we try to optimize forward KL and reverse KL, we'll get two different sort of a fitted, distribution with forward and reverse KL, right? So with the forward KL, it's sort of mean seeking and mode covering. So what it says is that wherever this P has a mass, Q should also have a mass, right? So otherwise, this log P by Q would be very high. So therefore, Q is it should spread out for all the modes. So that's why it's called mode covering or zero avoiding sort of a KL, right? And then we have for the reverse KL, basically the penalty is large where only Q have mass, but P is zero. So Q is allowed to collapse to a single mode to minimize this reverse KL. So this is like a mode seeking or zero forcing sort of loss, right? So KL is being used in different applications. You can see that in VA training. You can see that in the knowledge distillation, where student and teacher distribution it's done between the student and teacher distribution. Then it can be seen in TPO, TRPO in mutual information, and in the TSNE also that we see right now, right? That it's basically we're trying to minimize the KL between the P and the Q, where P and Q are pairwise, similarity distribution. So now coming back to the TSNE, right? In the TSNE, there is one hyperparameter, which is perplexity, and this perplexity is 2 to the power um entropy of the distribution, and you can think of it the effective number of neighbors each point used to fit its distribution, right? So let's see that with an example. If perplexity is small, you can see some sort of a scattered sort of clusters, and as you keep on increasing perplexity, you see this sort of a pattern in TSNE, right? So now there's another technique which is UMAP. So this has the same goal as TSNE. It preserves the neighborhood structure, but using a graph, right? So for every point, it finds the nearest neighbor and draws a fuzzy edge to each of them, right? A close neighbor gets a thick edge, and a far one gets a thin edge. And then what you do is that on the Y, you scatter the point, measure the closeness here in the same way. And here this A and B comes from this minimum distance knob or the hyperparameter, right? And finally, you try to minimize the cross entropy between the adjacency matrix of this V and W. So here you have two hyperparameters that you can play with while you're trying to visualize the data. So one is the distance, right? So here you have more, scatter sort of a visualization. And the other is on the nearest, neighbor. So if the nearest, this is a small, then basically we are sort of optimizing for the local um, structure between the data. But if we keep increasing this n to high a number, right, we'll also start getting some of the global pattern captured in the data. That let's see that again with an example. So suppose for this handwritten digit, we try to plot and compare, PCA, TSNE, and UMAP. So with PCA, you see different clusters, but the classes are overlapping. We are not very well able to segregate the data. With TSNE, we are able to segregate the data, but the pattern is local. It's like if 9 and 7 are sort of related, but they won't be very close in the space. But UMAP the intercluster distance here, it's not very sort of reliable that in TSN. But with UMAP basically tries to have this local as well as global pattern capture. And if you can see here, right, this some of the samples from this 4, 7, and 9 are close by, showing that they have a global. Some similarities between this data set. So That's we have discussed. So in this lecture, we have discussed SVD, PCA, and PCA is the SVD of the centered matrix. We have seen matrix factorization techniques, and we've seen the application of all of these methods. In Eigenfaces and topic modeling and Netflix recommendation problem. And we have also seen the visualization techniques like TSNE and UMAP. So these are, classical techniques of feature extraction. So next, we have dimensionality reduction in the age of LLM and generative AI, where we will discuss more recent dimensionality reduction techniques. So